Question number 18. So it is given that equal and opposite forces each F, two equal and opposite forces each F act on a rod of uniform cross-sectional area A. Please write the question also. Two equal and opposite forces in a cross-sectional area. From cross-sectional area A as shown as in figure shown as in figure. The shearing stress on the section AB will be the shearing stress on the section AB. The section AB will be. So the figure is given like this. This is the cross section. This is the block. And on this face, the force F acts. On this face, the force F acts. Equal forces acts in opposite direction. And it is given that there is a section AB. This is the section AB. This is the section AB. And it is mentioned that this make an angle X with the this side. You can take it as theta also. Okay. Sometimes in some books, different books will use theta as well. Okay. Then what is the shearing stress? You know, shearing stress is what? Shearing stress is nothing but a tangential force by area. So shearing stress is equal to tangential force by area. So here, what is the tangential force? What is the tangential force? Means this is the section. What is the force acting along the surface? The tangential force. So with this force, you can say this is the force. By symmetry, this is horizontal. The angle between this and this is x, right? What should be the component of this force? Component of this force normal to this and along this. If you say this is F, the area of this section will be in this direction. Area of this will be in this direction, right? So let us say by symmetry, you can say this is normal. This is x means this will be the total angle is 90, so this will be 90 minus theta. Similarly, so this is 90 minus this will be x, right? Asymmetry, you can say this is also x, can you say? So this is f is making angle x with this area. Its component along this is its component along a will be f cos x, right? And normal component will be this is normal to surface and along the surface is a normal one. So its component is f sin x theta. Theta is x here. That is the tangential force acting on this. Is it clear? You can say this is the one that is acting on the tangent. So this tangential force gives the stress. Are you following? So what can you say then? Uh, Here it is equal to, you can say that tangential force by area of this section, not this area. This area, let us consider area is A. A uniform cross-sectional area. This area is A. This area is A. This area is A. But what is its A? This area. So what you can understand? The area of this will be in this direction. So area of this will be in this direction. This you can say this is also making by symmetry. One second. Area vector along this area vector of this will be, you can take it as f tangential forces f sin x, but area of this will be taken as, this is A, Yes. Then if a component of A along the normal is nothing but A cos x. Yes. Is it A cos x? Or you can say area of this section is, let us take A dash. Hmm? A dash is equal to A cos x. But here this is area. Hmm? So this area is nothing but A is equal to area of that by cos x. Or you can take it as, or you can take this as area of A2 equal or opposite forces F each at an uniform order of uniform cross-section area A. So in terms of A only, then it will be if it is A dash by cos x. Actually, we are taking A dash by cos x. Then we can take it as area of cross section is A dash is A cos x. So we can take this as area of this section by cos x. This cos x it comes here. You can write it as f sin x cos x by the area of this section. Area of this section. Got it? So that is taken. We are taking here is we are taking this is area. A. So if it is this one, we will A dash. You can say this is A dash the other way. Not A dash. Here the symbols you can change. Hmm? So you can take it as A is equal to area of the section is equal to A dash cos x. So it is you can take it as A dash is equal to A by cos x and hence is A by cos x A cos x. So A f sin x cos x by A unit. Okay. So that will be the shearing stress produced in this. This is question number 18, right? Option 1, so that's really the right one. These are just you can work out. Okay, especially while finding this. Sometimes we will be asked to find a different other terms also. Even in terms of instead of giving this angle in this case here, you may be given this angle also. Right, so a similar kind of same question will be given if you ask for different other ways by changing the angle between the section and that's it. So next, I think then I'll ask a few questions. Is given as x. By symmetry, you have taken the other way earlier. No, actually, by symmetry, this angle made by this with horizontal and this with horizontal both are same opposite angles you can call. So this is horizontal, this is the direction, downward direction, this is x. So similarly, this is horizontal, this is downward direction. This will be x by symmetry, not this one. So this will be 90 minus x. So if this is f, tangential component will be f cos x. Tangential component is f cos x, not f sin x. F cos x and this area of this will be, if you take it as a and this is a, can take it as a dash, then a dash is equal to a cos this angle will be 90 minus x. A cos 90 minus x is this area of this section. So it is equal to from this a cos 90 minus x is a sin x. So a dash is equal to a by sin x. So here a by not cos x, a sin x it will be a sin x. A sin x. Then f cos x into sin x becomes f sin x cos x by a. This is the section. That's it. Estimate the changing density of water in the ocean at a depth of 500 meter below the surface. The density of water at the surface is 1030 kg per meter cube and bulk modulus of water is 2.2 10 power minus 10 power 2.2 10 power 9 Newton per meter square. So what is given here? Let's estimate the change in density. Change in density can be taken as delta rho is equal to what? Of water in the ocean at a depth will take it as h is equal to 500 meter below the surface. The density of water on the surface is density on the surface. We take it as on the surface rho 1 rho is equal to usually normal water we take it as 1000 kg per meter cube, but here for sea water it is given as 1030 kg per meter cube and bulk modulus of water is 2.2 into 10 to the power 9 Newton per meter square or Pascal equal to. then what is change in density and take. So bulk modulus is equal to, what is bulk modulus? Bulk stress by bulk strain, we cannot take it as a P by with negative sign when volume is decreasing, then take it as P by delta V by V, right? From this you can say delta V by V is equal to P by B. Till here okay. But you're asked to find the change in density. So yes, so you're asked what this is because your pressure is given, pressure at the depth of this much is asked, right? So at the depth of this, pressure can be taken as change in pressure uh, by B. The H is given, rho is given, G is given, right? Yes or no? So you can find out delta V by V. You can find delta V by V. But ask you can change the density. So how can you find that is? You're taking this and you can also density is equal to mass by volume. But when mass is constant, these are inversely proportional. By remembering the concept of equation fairness. So if you have something like y is equal to some constant a by x, and fraction error in this is equal to fraction. So if they are product or division, some of the fraction errors in the product of some of the fraction errors in the divisions. Using that, you can say delta if y equal to this, then you can take it as delta y by y is equal to delta x by x. If it is if y is equal to x into z, then delta x by x plus delta z by z. Sum of the fraction errors and all is equal to the fraction error in the left hand side part of the equation. According to this, you can say if these two are if proportional, if m is constant, then you can write delta rho is equal to delta v by v, delta v by v. So you can say delta v by equal to delta rho by rho. So from this, you can say this implies delta rho is equal to delta v by v into rho. So, but delta v by v is that. What is that? H rho g by b into rho. H rho g by b into rho. This is goes to elements. So H is what is it? H is given here 500 meters. Rho is density on all sides of a solid cube. Solid cube. This is a cube. This is a solid cube. Uniform pressure is exerted on normal sides of a solid cube, but it has 0 degrees Celsius. Initially, T1 is equal to 0 degrees Celsius. Right? In order to so as because of this pressure acting in all directions, the volume will decreases. So to bring the volume back to its original condition, we are increasing temperature T2 to T degrees Celsius. T2 to T degrees Celsius. Now, you have to understand that at T degrees Celsius, you degree Celsius, volume is bringing back to the original volume. Original shape is the change in volume by original volume it will be taken as actually change in volume is equal to proportional to original volume into gamma delta theta. Delta V by V is equal to gamma delta theta. Delta theta is final temperature minus initial temperature, or T minus 0 is T. So gamma into T. But you should remember that is gamma is volume coefficient of what is that? Thermal expansion. Alpha is linear coefficient of thermal expansion. The relation between them is gamma equal to 3 alpha. You remember this. Okay, then like if you take gamma equal to 3 alpha, this you can take it as delta V by V equal to 3 alpha into T.